Hello, hello. I'd like to welcome you all to the next talk by Seth Jenkins about some poor in-the-wild bug that has been found. Enjoy.
Hey guys, how's it going? My name is Seth Jenkins, and I work at Project Zero, and today I'm talking about unexpectedly excavating an in-the-wild exploit, talking about the Qualcomm DSP driver. And I want to start with a little bit of a story. And for this story, we need to go back in time. We need to go back to December 17th, 2023, and I want to introduce you to this guy. This is Ivan Bjelic, and this man, Luka Bjelic. And this man is an environmental activist and journalist in Serbia. And on December 17th, 2023, that they were having some big elections in Serbia there. And he's on a bus, and the bus gets stopped, and the police come over, and they arrest him off the bus. They take him to the Department of the Ministry of Interior. And they take his phone, and they give him a warrant and force him and compel him to turn over the PIN code to his phone. And they question him a bunch, and then they let him go, and they give him his phone back. And he gets his phone back, and you can tell his phone has been acting weird. He knows he's been targeted before. And so he hits up this organization called Amnesty International. And Amnesty International works with people all over the globe that are potentially oppressed by their governments and being attacked by their governments, helping them. And they actually have a forensics team that can do research on these sorts of things. And this research team found that there were some logs on these devices and determined that this tool developed by a company called Celebrite UFED was used against the device. And you can see here, this is just a brief sort of extract from their article that they wrote, and you can go look at this article online, talking about this man, Ivan, and the sort of work that he, some about what he was doing when he was arrested, and also talking about the technical details of how he was hacked. Right, and so this is pretty interesting. And once he got these sorts of exploit artifacts, there was a set of artifacts that were discovered on the phone, and those artifacts were turned over to Google's threat analysis group. And within those artifacts was a tranche of kernel logs from when the exploit crashed, but it did not actually include the exploit itself. It was just the logs, the kernel panics themselves, and the exploit itself was not available. And it's apparent from the kernel logs that the exploit triggered a bug in this driver called ADSP-RPC, but it's not entirely clear what exactly the bug is to Google Threat Analysis Group or to Amnesty International. And so those kernel logs ended up getting provided to Google Project Zero by tag for deeper inspection. And that's where I come in. Hi, my name is Seth, and I work, I'm a security researcher at Google Project Zero. And I primarily do Linux and Android kernel research. All right, we're off to a good start. And I also primarily focus on local privilege escalations. How can I get to root without using a password? And I've done some research in the past, both on in-the-wild Android exploitation and reversing in-the-wild Android exploitation. And I've also done some research into Android drivers. And so you could sort of say, like, Android drivers are my specialty. They're my area that I focus on. They're the part that I enjoy the most. And so when I saw this research that was going on and these sort of kernel logs, I was immediately super fascinated. And I'm going to take you on a journey today as we discuss all of these different kernel logs that were discovered. I'm going to discuss with you a lot of the bugs that I found. I'm going to then finish up by excavating an exploit, a possible exploit strategy, a hypothetical exploit strategy that was used by the attackers. And I'll then have some short conclusions. So I want to introduce you to kernel log number 1. It looks really small. Don't worry, I'll blow it up for you. There are a couple things to note here. Once again, we see this ADSP-RPC lines showing up. And we see a bunch of different functions getting called, and we're going to go through those functions in a little bit. And we also see this crash happening. Again, this crash is happening in fast RPC and map free. And this is an ADSP-RPC function. So again, it's pointing to this ADSP-RPC driver. This ADSP-RPC driver is important somehow to whatever exploit they're throwing. Okay. Here's kernel log number 2. Again, it's small. I'll blow it up. There's a couple things to note here. We see a lot of the same ADSP-RPC logs, but we also see this new one. From FastRPC and map free, we get this value here, invalid channel ID. And it's set to this value here, which is quite wild, because this value should never be higher than 4. In fact, if you go and look in the code, you can see that they're properly checking, hey, that value is never higher than 4. If it was higher than 4, it would be a pretty pretty powerful out of bounds. And so this value is pretty tightly constrained. So how are they getting this value so large? Like, what kind of bug is this? Like, is there some sort of bug in like how their channel ID management is going on? Like, what is going on here? But so we're looking at this, like, where is this value coming from? What does this number even mean? And actually, it was a breakthrough of Amnesty International to note that this number is, in fact, a date. If you plug it in, it's a Linux epoch timestamp in seconds, and that date corresponds to the day the exploit was thrown, December 17th, 2023. That's sort of interesting. Why should a channel ID be a date? That should never be the case. But so it is. Again, we have this crash log. We see it's in FastRPC file free. We know FastRPC and ADSPRPC. OK, clearly important. Next log, we see a lot of the same ADSPRPC messages, but we get a crash in a different place instead of where we were getting it before. And this time we get it in iNotify. What's going on there? How does iNotify play? Is there a bug in iNotify? There's been bugs in iNotify before. What's going on in that? Who knows? We just don't know. And then we have kernel log number 4. And this is doing some like pipe reads. And we see like pipe buffers getting used as an allocation primitive fairly frequently over the course of this. And so it's very plausible that pipe buffers were being used to reallocate memory and spray memory and control that memory. But so that's just what we have so far. But that's all we have. And so let's take a look at some of these FastRPC logs that we've seen, because it seems like FastRPC is kind of important. So we see there's 4 different log lines through the exploit. If we could sort of go through all the different logs and compile and distill it down to the 4 log lines that appear consistently. And each of these has a different function associated with them. And it's important to note, I think, that like at least 3 of these logs, it's really not clear why they happen at all, because they are triggering like really, really early function bailouts. Like the very first bailout you could trigger in the function before anything interesting happens at all. And so it's not quite clear to me even now why they would do this. But we do see that this line, FastRPC mmap free, that one looks really interesting, and it looks fundamentally different from the others. We sort of get this idea from looking at this. Okay, it feels like maps are important somehow, but it's not clear how. But let's go deeper into this FastRPC mmap free, because it's the one that seems like it has more information for us. So we sort of get this idea from this line that FastRPC mmap free is important, because we have like these invalid channel IDs, because we see crashes as well happening in FastRPC mmap free. And so we sort of get this idea of FastRPC mmap structures seem important somehow. And these are actually like just structs. They're k-malloc. We'll talk about them a lot. But suffice to say, despite all of this, it was like, okay, I don't feel like I have enough to figure out what the bug is. Like I've learned some interesting details. It seems like FastRPC mmap structures are involved. Maybe they're part of the exploit. Maybe they're part of the bug. I don't know. It doesn't seem like enough to figure out what the bug is. And I ended up just giving up. All right, I'm not going to be able to figure out the exploit right now. And so I decided to switch strategies. Instead of looking for the specific bug that was used for the exploit, I decided to widen my focus. Let's just go back to first principles and find any bug in the ADSPRPC driver in general. Any bug will do. I don't care what the bugs look like. This is an interesting driver. I like drivers. Let's hack on it. And let's learn a little bit about this ADSPRPC driver. That turned out, fact of the matter is, that turned out to be a very good decision. I found 5 different bugs over 2.5 months. I'm going to discuss several of them today with you. So let's discuss this ADSPRPC driver a little bit. ADSPRPC stands for Application Digital Signal Processor Remote Procedure Call Driver. And I'm not going to say that again for the lifetime of this presentation. That's once is enough. It's reachable through this file /dev/ADSPRPC-SMD. And it's reachable in untrusted app context, which makes it particularly interesting from an exploitation perspective. It acts as a liaison between the application processor and the digital signal processor. So that involves, like, when you want to make a remote procedure call in the digital signal processor, you talk to this driver, and it will help you manage like all of the memory mappings for that, the buffers, sharing those memory mappings between like your user land and the digital signal processor, all of that sort of fun stuff. And the complexity of this thing is pretty high, because it has to manage all of these different things, and also like you have to be able to like send it arguments, and then you have to receive data from it, and it also supports like asynchronous execution of these remote procedure calls. So yeah, there's just a lot to handle for this. There's a lot of complexity, and that makes it interesting to hack on. And this was the first bug that I found. And it's good, like we look at this macro here. I remember looking at this macro one day, hanging out in a call with a colleague of mine. It's k copy from user. And it takes this parameter, kernel, and based on this parameter kernel, it decides whether or not to make a copy from user call or a mem copy or a mem move in this case, but it's the same thing for the purposes of this presentation. Yeah, so it's just like based on this parameter, it's choosing whether the pointer is from user land or kernel land. That's sort of a weird behavior. I feel like I wonder if there's ever be a case where this could like get flipped around somehow, where they use the wrong parameter in the wrong case and end up accessing, using a user land pointer as a kernel pointer or something like that. And then I noticed, just later that day, this flag here, FL is compat, which is passed directly into kcopy from user as the kernel parameter. Okay, so where is this flag getting set? And by the way, FL is just associated with like the file descriptor. So for any of you, you could probably already start figuring out where this is going. This flag is just set when the 32-bit ioctal interface is invoked. And this is bad because just because you invoke the 32-bit ioctal interface on the file descriptor once, that doesn't mean you're going to invoke the 32-bit ioctal interface on the file descriptor again. You might invoke the 64-bit ioctal interface on that file descriptor in the future. You can intersperse these calls between 32-bit and 64-bit, no problem. But when this FL is compat is set to true, like that's it. Like it's just set on the file descriptor. It's actually set for the lifetime of that file descriptor. It's never unset. And so all you have to do in order to trigger a really nice kernel splat is trigger the 32-bit ioctal interface once, and then make a 64-bit ioctal call. And it ends up expecting the call to be coming from 32-bit, that 32-bit marshalling layer, instead of 64-bit userland. And we get this really, really nice kernel splat. And we get this perfect virtual address of 41414141 and like really nice like potential arbitrary read primitive. So this is very encouraging. There's bugs in this driver. Let's go find some more. For the rest of the bugs, I want to talk about this structure, fast RPC mmap. We're going to be talking about this guy a lot. And you can see this is just sort of a brief layout of what one of these fast RPC map structures can look like. There's important things to note. One is that maps can be stored on a couple different lists. I've got two maps here, map A and map B, and you can see that in one case that's on this global list called GFA, and in the other case it's on this FL list, which is associated with a file descriptor. Right? And then you can also have these like context-based arrays, and contexts are what you use whenever you make a remote procedure call. So every time you make a remote procedure call, new context is created. And so these arrays are sort of like transient arrays just associated with that remote procedure call. And so, there can be a lot of different kinds of references to these maps. And so in order to manage that, there's actually two different reference counts. One is refs, and it's used for all references, both contexts and non-contexts. And there's another one, context refs, which is used for references by context objects or arrays. So there's actually two different reference counts floating around. And also it's important to note that like for the context sort of references, there's actually two different possible ways that maps can be referenced by a context. One is as either a buffer or a handle. We're going to talk more about that later. It doesn't matter yet. But they're also both stored on this maps array in a context. So yeah, if this feels kind of complex, all right, there's a lot of things floating around here. Yeah, it felt complex to me too. That makes it great for finding bugs in. And let's talk a little bit about this function. This is fast RPC mmap create. And this is the function that creates a map. But turns out it's a little bit actually of a misnomer. It doesn't only create maps. It first tries to find an existing map that fulfills that request. And it makes this call fast RPC mmap find. And you can see that if this fast RPC mmap find call succeeds, it just returns. It doesn't actually allocate a map. And if it succeeds, it will just take a reference on the existing map. That's what fast RPC mmap find will do. Here's what fast RPC mmap find will look like. It's a little small. Hopefully you can read it. You can see that there's a couple interesting things here. One is that mainly that you can see that the map is sort of compared against every map in either the global list or on the FL list is compared against a set of certain things. That is that the virtual address is in range, the length is within range, and the file descriptors are the same. And if that's the case, then it's like, great, this map fulfills the existing request that you asked for. Let me just add a reference to this and return that map. Great. And then only if the map does not exist does FastRPC map create actually go about creating a new map. And when it does create a new map, it kzalix it, just a general purpose kernel malloc. And then it also adds that map to the FL local or the global list, depending on the flags that you pass to FastRPC and map create. Great, so now we have enough information, we can talk about another bug that I found. Again, this is FastRPC internal mem map, so this is an ioctl call that you can make, and it's for mapping memory. That's what its purpose is. It's pretty straightforward. And of course, as you might expect, for something that's mapping memory using these struct FastRPC maps, it calls FastRPC map create, to create a mapping. Okay, so that makes sense. And again, we also want to look at this like FastRPC map add function a little bit deeper. And this is the function that gets called at the end of FastRPC map create. We saw it before on the slide before. And you can see that there's like 2 different cases here. You can see one of these cases involves, if it's a global array, and you can see it's added to this array called it's global list called GFA, and you can see that if these certain flags are attached, these are sort of global flags, the map is added to this global list, me-caret maps or GFA-caret maps. And in this case, it actually takes some extra locks here, the spin lock IRQ called hlock, right? And in the other case, if it's just putting it on the local FL file descriptor list, it'll put it on the FL-caret maps list. Okay, so that makes sense. And then we have this other reciprocal function, FastRPC internal mem unmap, and this does the opposite of internal mem map. Again, we actually see that these calls here and we see these in both FastRPC internal mem map and FastRPC internal mem unmap. We see these calls to locking some mutexes here. To make sure theoretically that there's no concurrency. You don't want things being added to the same map, the same list at the same time. We have this FastRPC mmap remove, which actually just removes it from the FL list or the GFA list. And then we also have this FastRPC mmap free call. And that removes it. That actually destroys the map. And in FastRPC mmap remove, you can see here, again, we have this sort of spin lock being taken, this hlock. And then we have the map being looked for. Again, it's just using the virtual address. Is the length within range? Is the references equal to 1? Okay, great. Yes, it's the map that I was looking for. Here's the map. We remove it from that linked list that we were talking about before. That's either the global list or the FL list. And it just returns it back up to the caller. Okay, great. So this seems a little bit weird because this actual global locking is only taken in a couple places. And it's not taken throughout the lifetime of FastRPC internal mem map. It's only taken inside of FastRPC map create for that brief sort of moment. And that feels weird because it means that concurrency isn't really prevented if you're having 2 separate file descriptors, 2 separate opens of ADSP-RPC-SMD. So if you open this file twice and you both operate on the same global list, that's like sort of allowed. And the concurrency protections that we have, internal map mutex and map mutex that we see at the top of this function, doesn't really protect you. So if we have a FastRPC map create call that creates a global map, and then we have immediately after that a FastRPC internal mem unmap call that references that global map and tries to destroy it, there's nothing that actually prevents this. The global locking is not actually protecting against concurrency of that sort. And it's possible that FastRPC internal mem unmap can destroy the map immediately after it's created before FastRPC internal mem map returns. And then we have a bunch of later accesses to this map later in the FastRPC internal mem map function. And this is just use after free. We're just using these maps after the map was destroyed with FastRPC internal mem unmap. And normally this race would be prevented by these map mutexes. Like you couldn't do this if you just opened the file once and was doing this on the same file descriptor on like 2 forked processes. But because we're operating on that global GFA maps list, we can just have 2 separate FL structs, and they can currently access the same list. That's totally fine. And this map mutexing doesn't protect us from these global sort of races. So, okay, bug number 1. We get this really nice crash. Feeling pretty good about it. Our first use after free of the day. And now I want to talk about this other bug that I found. Again, we have this, I want to go back and look at these mem mapping functions. And this time I want to look at FastRPC and map remove a little bit deeper. And I want to note something about it that we didn't note before. which is these separate calls in here where we take a reference to a map, or we check to see if the references is set to a certain value. That is, we must verify, okay, there's only one reference to this map, and map context refs is equal to 0. Okay, so there's no context references, and the reference is equal to 1. And only in this case does fastRPC and map remove actually remove the map. In any other case, we just fail out and say, oh, sorry, we can't find the map, right? So this fastRPC internal mem unmap function really guarantees that the map is in a very specific reference counting state before it will remove and free the map. But we have this other ioctl call, fastRPC internal fastRPC internal munmapfd, and it does something a little bit different. It used the fastRPC map find. We've talked about it before. It will find any sort of map that is, matches with these sorts of requirements. The virtual address is in the range. The length is the same. File descriptor is the same. And if that is the case, then it will just return that map. And then later on, we have this check to see if this attribute flag is set. And if it is, then we just unset it and call fastRPC map free. We don't have the same protections that we had before. It doesn't check to see if references is 0. It doesn't check to see if there's any context references. It just calls in map free. And that seems sort of weird. So like, how does exactly this map attribution work? And we can see that this attribute is set like at the beginning inside of fastRPC map create after a map is created. It actually is creating a map here. It's not just finding one. This is only during actual map creation. And we also see later on, if that attribute is set, then we set map refs equal to 2. And we set it in this final else block of this if else case. And only in that final block. But fastRPC adder keep map, this flag that is used in both fastRPC internal munmapfd and to make sure that reference is set to 2, isn't actually disallowed in the other two cases of this if block. And that means that like if you set both fastRPC map fd no map and fastRPC adder keep map, the references stays set to 1 instead of getting set to 2. And that just feels like weird to me. Like my spidey senses are tingling at this point. Like something about this behavior really does not seem right. So I can create a map with only one reference, which is not supposed to be something that you can do, that can have a reference dropped with fastRPC internal munmapfd. This is not like supposed to happen. And fastRPC internal munmapfd doesn't provide these guarantees that the other unmapping functions provide. That is, references is set to 1, context refs is set to 0. That is, there aren't any contexts associated with the map. So that means that like if I could achieve this layout, and this layout is like, okay, a context does have a reference. In fact, it holds the only reference to a map. I could potentially cause a crash because if it was at specifically this point, if I called fastRPC internal munmapfd, we would remove the last reference for this map, and that would end up destroying the map. But context would still have a dangling reference to that map. But it's not quite clear how to create that sort of layout. When we create these maps, there's a couple different ways to create them. But if we create one via fastRPC internal mem map, this behavior is very easy to get. I can just call, if I just like make a mapping, this is the normal behavior. And if I were to add fastRPC adder keep map, just that flag to the map, we get this sort of behavior. We can see references is set to 2 here. And now if I add the second flag, fastRPC map fd no map, then references is set to 1. This is the weird behavior, but I can't figure out, it's not immediately clear how exactly to utilize that behavior. But now if I were to take this map and then I were to have a context take a reference to it, the context would take a reference to it, and I would add another reference to this map. And this is not quite the behavior I want, right? I'm looking to have that reference is set to 1. In this case, the references is set to 2 with these flags set. This isn't quite right. And so now if I were to call that fastRPC internal munmapfd, the references would be set back to 1, which is correct, and then the context would be fine. The context would clean it up when the context gets destroyed. So, okay, so how can I take advantage of this? I can only create these mappings of fastRPC adder keep map and fastRPC map fd no map. These mappings I can only create with this one ioctl, fastRPC internal mem map. I can't always create them. I can't create them, like, for example, during context creation. During context creation, I can also create maps. But if I want to create, and in fact, the benefit of creating it during when I create a context, when I make a remote procedure call and the remote procedure call creates a map, that you can also do that. But the problem is that if you do that, then you don't get access to that specific cocktail of flags that I need in order to create this very weird case mapping. So it's quite easy to get this behavior, right? Where, okay, reference is set to 1, just how I like it. A context has a reference to it, great. But you can see that the flags aren't set on this. So how can I achieve this? Turns out there's a way. I'm looking for this layout. I have this layout. How can I make this layout happen? And the way that you can do it is you start in FastRPC internal mem map. And we have this FastRPC mmap create call. And we create a map with this cocktail of flags. And we get this behavior. Okay, this makes sense so far. This is the weird behavior that we shouldn't have, but we have. And then let's say we concurrently have a context creation that calls FastRPC mmap create. And let's say that FastRPC mmap create takes a reference on that previous mapping, that FastRPC internal mem map just created. We talked about that before as well. And now we have this behavior, which we've talked about before. References is set to 2, context has a reference, and then we also have the reference that FastRPC internal mem map just created. But remember, these are running concurrent in this case. And so FastRPC internal mem map could still be executing at this point. And it could hit this call, FastRPC mem map to DSP. And let's say that this call fails. If this call fails, then we just go to a bail. And when we go to bail, we just hit FastRPC mmap free. And FastRPC mmap free won't immediately free. It'll just remove a reference from the map. And that ends up with this behavior, which is just the behavior that I was trying to trigger to cause a crash. And then if I call FastRPC internal munmap FD with this, that references get set to 0, the map gets freed, but the context still has a reference to the map. And we get this really nice crash like this. Great, we've now got 3 different bugs. And again, we have this great sort of here's the crash trace. I've blown it up a little bit. You can see there's this FastRPC mmap free call. And it was about this point that I started to notice that something about this seems sort of kind of familiar. And then I remembered looking at the in the wild exploit, and we could see that the in the wild exploit, we have the crash, and the crash from the in the wild exploit also happens in FastRPC mmap free, just like my crash does. That's sort of interesting. And turns out that, okay, my crash looks a little bit different below that, it's not happening during FastRPC file free. But actually, it's not actually that hard to get my crash to look similar to this. And turns out that this exploit, this specific proof of concept, this bug only worked against a newer kernel version than the one that the in the wild exploit had. But it does feel okay, I'm getting close. I'm generating a crash that looks super similar to the in the wild crash. And now I'm starting to think maybe I'm actually getting pretty close to finding something that might have been related to the in the wild exploit. Yeah, so what are the sort of ideas that we have about this in the wild exploit? We see that there is this crash in the FastRPC mmap free call. Now knowing that we know a little bit more about this driver, we know, okay, the in wild exploit is causing this wild map value for the channel ID. And so it actually seems now with a little bit more thought, the in the wild exploit is probably causing a FastRPC mmap use after free, one of the just the same sort of bug class that I've been finding with the last 2 bugs, and I actually have 2 separate FastRPC mmap use after free bugs at this point, but neither of them seem quite right. The last one doesn't work. The kernel version is too new, and the one before that generates sort of log lines in the exploit and the proof of concept that I don't see in the wild exploits. It doesn't feel like it can be the one. So let's keep looking. Let's just keep looking for more bugs. And then I want to go back to this function. We looked at it a little bit before. This is the function that happens during context creation. And we can see that, again, we noted that a context can reference a map in 2 different ways. One is as a buffer and one is as a handle. And in the buffer case, it does this. It just calls FastRPC mmap create. And it puts that value into this array CTX maps, and it just puts it at a certain index. And it just acquires a reference to that map just like that. And this is how maps are referenced if they're buffers. And then later, when those buffers are dropped, it ends up just destroying it like this. It looks for that map in the array, CTX maps, calls fastRPC map free, drops a reference on the buffer. We're all good to go. In the case of handles, it looks a little bit different. Again, we have the same sort of behavior here, where we have fastRPC map create. But during dropping, it looks a little bit different. We have this fastRPC map find call instead. And it's using this, a file descriptor that comes from this array, and that array is getting populated by the digital signal processor. And fastRPC map find, we've talked about this function quite a bit, it's going to find a map on the FL list, a map on the FL list, with the associated file descriptor. And that leaves a question. This is like super different from how buffer references are acquired and dropped, and it can find any map, right? So how do we know that the map that we find with fastRPC map find here is the same map that we acquired a handle reference on earlier? And that's the neat part, is that we don't do that at all. So that means we can actually generate, if we do the following behaviors, if we create a map A, and we take a reference to map A as a handle from a context X, and then we create a map B that collides with map A, and then we take a reference to map B as a buffer from a context Y, and then we finish using context X. That's going to, because I took it as a handle, it's going to call this and put args, which is going to call fastRPC mmap find and end up just calling fastRPC mmap free. And it's going to find, instead of finding the map A, it's actually going to end up finding map B, since map B collides with map A. And map B ends up getting a reference dropped instead of map A. And that means that context Y is left holding a dangling reference to this map B that just got freed when it wasn't supposed to. And I get a really nice crash here. And again, we see this super similar looking crash. Again, it's in fastRPC and map free. Here's the in the wild comparison, so that you can look at them and be like, oh, yeah, I mean, kind of. And we also, if with a little bit more effort, I can make the crash look even similar, where like basically the whole bottom half is shared, where we have it in fastRPC file free and fastRPC and map free. And so it's like, okay, I can like, I feel like these crashes are different. Yes, it doesn't look exactly the same, but that's kind of to be expected, even if I was hitting the same bug, because they're trying to actually write an exploit, and I'm just like, screwing around on my computer. And it's also important to note that actually this bug would have worked on the same kernel version the in the wild exploit used. And there's been actually several different bugs now. There's been like 4 different fastRPC mmap use after free issues that have been found. And out of all of the ones that we found, Qualcomm and I agree that this is the most promising vulnerability that would have been potentially used by the in the wild exploit. And for that reason, we chose to report this vulnerability as in the wild. And I think it's important to note that, having talked to a bunch of different people in the industry, it's clear this driver was being used by attackers, right? We are quite confident in that. And so I think it's fair to say that, like, maybe even treat all of these bugs as potentially being exploited in the wild in some sense or another. And I'm fairly confident that all of the bugs that were solved and remediated as part of this effort had a significant impact on preventing in the wild exploitation. So after I did all of this, I decided I wanted to go and see if I could like write an exploit for one of these issues. And that turns out to be harder than I expected because I don't have an info leak, and info leaks are kind of important. And so in order to be able to actually achieve an info leak with the same bug, I wanted to find like some compatible heap spray object that would give me some sort of like interesting sort of potential leaking of like the ASLR slide or something like that. And that turned out to be a lot harder than I expected. Frankly, I just failed on my own. And I remember waking up one day and like remembering this message that we saw in the in the wild exploit with this invalid channel ID with this crazy value. And it was like, wait a second. Like that the exploit, the in the wild exploit is causing a fast RPC mmap use after free. It's causing this sort of channel ID. Now it's like, okay, that's got to be memory corruption of some sort. Like, it seems likely that this invalid channel ID value is coming from whatever object the attackers heap sprayed. What if I could find that? What if I can find that object that the attackers used? Could that object be what the exploit used? And so now I have a new task. I have a new mission. Instead of looking for my personal my personal object to heap spray. I'm looking for what object did the attackers heap spray, and that means I'm looking for an object with a timestamp at a very specific location. I ended up doing quite a bit of like work here of just like looking through all of the objects in the Linux kernel, like looking for objects with timestamps at like maybe just the right location. I wasn't having a lot of success with that, but I had this idea of like maybe I can find one. And again, we're looking for like this sort of behavior, right? So like, okay, we have the map and it's getting this reference FL, and then from like offset 16, and then I have this offset 104 into that, and at that is the channel ID, but it's getting set to this crazy timestamp value. So I'm looking for some sort of object that like matches this sort of hierarchy. And has a timestamp at that location. And the question is, can I find some sort of sprayable object where at object plus 16 dereference plus 104, I find a timestamp? And then after doing some research and not really having a lot of success, I had another moment of like another eureka moment. Wait a second. We had this earlier crash from iNotify handle event. And it happened during a kmalloc call, right at the point where the exploit would have been heap spraying. In fact, it happens at just the right point, right before the channel ID messages would have shown up. Maybe that iNotify object might be the object that sort of fits the bill. So let's look at this iNotify handle event call a little bit more. This seems worth looking at. Let's look at what exactly is iNotify handle event kmallocing. And we can see that if we look in iNotify handle event, we have this creation of this iNotify event info object. It is, of controlled length by the attacker based on the name of the file that was passed into the iNotify, which is great from an attacker perspective. And then we have this nice kmalloc down here. And so let's look at this iNotify event info struct and see what we find at plus 16 plus 104. So we look at this iNotify event info, and we see that the first thing is fsNotify event, FSE. Okay, so in order to see what's at offset 16, we need to look inside of this. And we find at offset 16, there's an inode pointer. Okay, great. So now we need to dereference the inode pointer and see what's at inode pointer plus 104. And we see that when we look at that, we see that there's a time spec value, I_m_time. And if we look a little bit deeper into that, what's at 104 actually, when we look a little bit deeper into that struct, we see that it's a tvsec value, that is to say the epoch's timestamp for when that file was last modified. And now this makes so much sense in the context of invalid channel ID. Like, this is why, almost certainly why, this timestamp value is showing up. It's because iNotify event info objects are getting put in that sort of place where the fast RPC map was used after freed. And we've actually seen some stuff using this object before to achieve, in this case, like we've seen it used to achieve an info leak, and it's plausible that that's what the attackers are doing here, although it's not entirely clear. But it's definitely the case that, it's almost certainly the case that they're using iNotify event infos to heap spray over these fast RPC maps. So that's super cool. And then again, we had this like pipe read, and this could be potentially used to actually take control of the object, perhaps once they achieve some sort of info leak or something like that. We've seen this before. Pipe buffers are a common exploitation primitive that are used to achieve control over memory. Great. So there's a couple unsolved questions that I would still have, though, when it comes to like how this thing works. One is like, why does the exploit generate those first simple errors? What's going on with that? They don't seem to be doing anything. Two is, how does the exploit crash at the iNotify allocation time? Because if it's crashing at that point, that means that there's some sort of heap corruption happening before that point. And there's still questions about how that works. It's possible maybe it was from the exploit being thrown multiple times and there was already heap corruption or something like that. But it's not quite clear why this sort of crash happens. And it's also not quite clear how the crash is happening during FL maps list traversal. And it's also like, if we actually look in the logs, we see that we generate a bunch of these invalid channel ID messages per throw. And it's not clear why that's happening either. There's also like multiple seconds between these invalid channel ID messages, like sometimes like 10 or 30. Like, why is that happening? That's not clear either. And so if any of you happen to know why they did this, come see me after class. And I think my pointer just died. What? There we go. Back to our feature presentation. So I want to talk a little bit about patch timelines here. The first bug, this was the FL is compat issue. It was reported June 11th, 2024, and it was fixed October 7th, 2024. That means it took 118 days to get patched. As a reminder, Project Zero, our goal is to try and get things patched within 90 days. That's our disclosure policy. That's pretty industry standard disclosure policy is having patches within 90 days. So 118 days is unfortunately above that. We had this other bug. This was the first fast RPC and map use after free, and that got fixed after 70 days. So that looks a little bit better. And then we had the internal munmap FD issue with that cocktail flags, and this one took 257 days to get patched and only got fixed like a month and a half ago. And then we have the final bug. This was the in the wild bug. This one had the shortest timeline. It was fixed in 53 days. All right, 50%. That's like bad, but it's not. Like, it could be worse, right? Well, it's actually, let's make it worse. Let me add some context here. Both of the bugs that were fixed within deadline were actually duplicates. The first one, the first mmap use after free, was the fix you can actually see in like their public repos. It was fixed on May 27th, 2024. It was written by that date. And that means that from the point that the patch was written to when it was released was at least 99 days and probably more. And we also have, for the In the Wild exploit one, that fix was written by June 27th, 2024. And that means it was at least 102 days from the time that patch was written to when it was released. And we also see that that's only when Qualcomm releases it, and then Qualcomm releases it in their security bulletin. When Android actually gets those fixes is even later still in some cases. For the first issue, it wasn't until 146 days that the issue got patched. And for the In the Wild issue, it was 130 days before it got released into the Android security bulletin, at least from the time that the patch was created. So that means that actually from the moment that Qualcomm finds out about any of these bugs to the moment that the bugs get patched, none of them got fixed in 90 days. Several of them weren't even close. So what's the conclusion? Like, we've learned from all of this that cybersecurity we've known for a long time that cybersecurity is only as strong as its weakest link. That's just true for any sort of privilege boundaries. And we've been talking a little bit about or exploitation for Android drivers quite a bit. Project Zero has talked quite a bit about it. We've also had Tag talk a lot about it as well. Okay, the most common exploits that we see are GPU drivers. Android Offensive Security blog has talked about it as well. And then if we expand even beyond Android, we also see like a lot more cases if we look publicly of exploits being thrown against these Android drivers. And so this leaves a real question of like how can we improve Android drivers so they stop being like the principal attack surface that attackers are using in the wild? How can we improve this particular weak link of the local privilege escalation security on Android devices? And we see that like there's a couple big issues here. One is that a lot of these drivers are developed without really being designed for user security first. They sort of come from a different age where the trust was implicit on user land, and a lot of these drivers are sort of built up on top of that, to fix bugs and stuff like that, but weren't really designed with user security in mind. So this is one thing that it would be better is to just see drivers that are developed with that sort of idea front forward of just like let's develop a driver that doesn't trust userland so much. We also see like not great code review processes for these things. Finding the code for these drivers can actually be sort of difficult. It's certainly not as easy as finding the code for like Linux mainline. They can be buried in like awkward sort of places. And really there's just like we see a lot of research on them, but it doesn't seem like there's like a sort of long-term accountability of a code review process going on here. And the biggest issue that we see with these drivers is really a really long supply chain. And this is the big reason why these drivers are taking so long to get patched, because it's, the Qualcomm releases it, and then it ends up in the hands of OEMs, and then it ends up in the hands of Android, and then it's like has to go through so many different gates. And so actually being able to like minimize these sort of patch timelines is going to involve, some fundamental changes to how we manage the supply chain in order to expedite those patches through the system and make those patches get released quickly. So thank you. That's all I have. I think I'm at time, so I'll skip the demo, which was boring anyway. Oh, wait. Actually, what am I talking about? I'll subject you to the demo because I have 15 minutes. So I'm going to drag this over here. And this exploit is not complete, by the way, just to set expectations appropriately. This exploit is just demonstrating that I can like generate crashes with the same sort of invalid channel IDs set to timestamps that the in the wild exploit does. So if I go here and I just run this sort of exploit, this exploit is just going to use after free these objects and then spray iNotify event info objects. And that's all it's going to do. It's just going to drop those objects and then spray it on the same CPU core. And that just, there we go. So let's run this a couple times just so that we have a couple of those logs. And then let's just crash the phone. This is the first version of the exploit that doesn't work. And at some point, this should crash, except it's not going to for some reason. Let me push this back to the phone here. Nope. Yeah. Well, you guys don't get to see my party trick after all. All right, fine. I'll just show you like an example log instead of doing this crap. So like, I can get this phone to crash. Probably if I ran this in a while loop, it would crash eventually, but let's like not do that. Instead, let me just show you an example log that I can generate with these. That's interesting. I've never gotten that particular failure case before where I just can't get it to crash at all. Oh no, I've done it wrong. Now I have to get a crash. Fine. We have time. You guys can just sit and wait. It's fine. There we go. So one thing to note about this crash is that it's happening. You can see that I've printed here the access time, the modify time, and you can see there's actually two different values here. One is the seconds values. One is the nanoseconds value. You can see the phone reboot here in a moment. There it goes. I just heard it buzz in my hands. I would love it if like I was printing the seconds value because like that would look like even cooler because then it would look exactly the same. But this phone like ends up that like inode struct is like offset by 4 in this case. So I end up printing the nanoseconds value instead, which is unfortunate, but that's fine. So as this phone reboots, we're going to look for this value 583. I can't read it. 8516 in the logs, and we'll see that show up in the logs when the phone reboots. And now while the phone reboots and then I call get kmessage, this would be a great time for questions, if anyone has any. I mean, we can all just stand here too, that's fine too. Turns out that generating a bug report takes a while. I wish there was a faster way to do this. There is a faster way to do this if you have a rooted phone, but like if you don't have a rooted phone, like the easiest way to get crash dumps is just to like call ADB bug report, which takes like 3 minutes. So.
Hey.
But the good news is I'm still like 12 minutes behind time, so.
Can I?
But yeah, again, if anyone has any questions, this is a fine time.
Oh, yeah. Hey, thanks for the great talk. So I was wondering, maybe that's actually not a question to you, but since the problem is like with supply chain, right?
With what?
With supply chain. I mean, that's like a Qualcomm stuff, so something like Pixel or Google is actually buying this stuff, right?
Yeah, there's a lot of different members of the supply chain, and Google is one of them. Yeah, absolutely.
So if they are doing their job bad, why isn't Google like asking them to do their job well, or maybe even offering like code review or helping with that?
I mean, maybe this is Google asking them to do the. No, I'm kidding.
Yeah.
No, I mean, I think yes, it's a very complicated supply chain, and and to some extent, Google is asking for improvements in how fast we can do this. I think there is desire to put pressure. There is sort of an idea in the industry that it's like not really possible right now to make this go faster. And I think can be some sort of acceptance of like, oh yeah, that's just the case. It just takes a while to get these fixes. But I don't think end users really like that's how they're thinking about this, right? They're looking for they're looking for actual fixes within 90 days, hopefully. At least that's what I'm hoping for. Okay, so we're getting these crashes now, or we get back our kernel panic logs. We can see actually that like we're generating a lot of different invalid channel IDs. I think some of these are coming from like because I'm like hitting some other object instead. I've never seen that sort of crash. Actually, some of these it looks like it's actually hitting like the right value, which is like the seconds value instead of the nanoseconds. I'm not sure how that's possible, but we can also see crashes here where we're getting these sort of 863 values here, along with a whole bunch of other different values. This is a weird demo. I've never seen it do it that way before. But you can also see we get this this kernel crash that's happening in like FastRPC as well. And normally it happens in FastRPC mmap use after free or FastRPC mmap free, but Murphy's law is strong today, so yeah, we get. Oh, there we go. Yeah, so we do get the crash in FastRPC mmap free. So yeah. Anyway, that's the lame demo. If anyone else has any questions, yeah, feel free. Sweet. Thank you, guys.